Okay. Okay. Melee? So thermal expansion and contraction. So we've talked about this a little bit. Remember, all things vibrate. All things are moving. Even solids, they're vibrating around. Well, let's take a solid. Think of all the little atoms on little springs. If I cause it so as they're vibrating, do they get a certain distance apart? I mean, they're vibrating like this. Are they all getting a certain distance apart from each other? Yeah. What if I add some energy to it? They're going to start vibrating more. Are they going to stay the same distance away, get greater distance, or get closer? It's going to get greater distance. And you might think, well, one little atom getting a little distance apart, that's fine. And you're right. It's going to be a little bit. But in your tabletop, how many atoms are there? Billions and billions and billions of little atoms and molecules, each getting a little bit farther apart. It builds up. So as we add energy, the molecules we're going to expand. As we remove energy, they're going to contract, with one exception. There is an exception to that rule. Anybody know what that exception to the rule is? It's one of the most common substances on the face of the earth. Water. And water over a small range of temperatures. There's a reason. We'll talk about that here during class. But the movement causes our molecules. This is why we have things like this in a bridge. It's called an expansion joint. Now this type of expansion joint, a lot of times the expansion joint might just be a line. So in that gap. In fact, if you looked at a lot of overpasses and things like that, you notice the gaps are very wide right now. The gaps are wider. Why is that? Well, because it's cold out and everything's contracted, so they get wider. In the winter, those expansion joints get wider. In the summer, they get narrower as the thing expands on that. So, on that. But it's why the little things are there. It has teeth, so even though the gaps are getting bigger, you still have something to drive on. And something like the San Mateo Bridge, they just have one expansion joint? No, they have lots of them. Because although, I mean, we're not talking a lot of difference, say, between a summer and winter temperature. You might be talking only 1 or 2 millimeters. That doesn't sound like very much. But that means for every meter of concrete, it's changing maybe 1 or 2 millimeters, even though it's just 1 millimeter. But the San Mateo Bridge is 10,000 meters long. Each meter changing 1 millimeter. Pretty soon, that's a change of 10,000 millimeters. That's a 10-meter gap. Would you want a 10-meter gap appearing in your bridge? No. Unless you're like the Dukes of Hazzard and over the top every day. That would not be any fun. So they break it up into little pieces. If you took the difference in all the gaps here, yes, would you get to that 10 meters? Yes, but each gap is very small on that. Same thing with our other bridges. Also, you'll notice freeway bridges, if you went underneath this bridge out here for 280, you have the overpass. Look at it closely. You'll notice that one side of the bridge is not attached to the other. In other words, it just sits there. One side's attached, the other side just sits there. It's usually, if you look, has a little thing that kind of looks like this. You would see, kind of looks like that. Why is that end allowed to move around? Well, as we expand and contract, it has to be able to move, because if both ends were solid, if it keeps expanding and contracting, well, if you take a paper clip and you keep going back and forth, back and forth, back and forth, eventually what happens to it? Snaps. Same thing would happen if we didn't give it a place to expand and contract. Eventually it would rip itself apart. Even the Missouri superstructure was so large that they actually had an expansion joint in the middle. So as during the day and night, it would expand and contract. Made a lot of noise too. I had a stateroom right next to the expansion joint at one point. You know, my bedroom on the ship, and you would hear it all night long. You wouldn't really hear it during the day because there's a lot of noise during the day, but at night you would hear the thing creaking as the ship was contracting. You would hear all this creaking and popping as that expansion joint was getting bigger. And usually there was like a rubber gasket in it that kept everything nice and watertight on that. But this is what happens to materials. They'll expand and contract on that. I got a little video about that.
This process is called evaporation, the change of state from a liquid to a gas. When gas molecules are cooled, they go slower and crowd together more densely to form a liquid. This process is called condensation, the change of state from a gas to a liquid. And now, expansion and contraction. If you blow a balloon only partly full of air and leave it in the sun, it will get quite a bit bigger. If you take another balloon and blow it up as hard as you can, and then leave this balloon in the sun, it will very likely burst. Why do balloons get bigger and sometimes even burst if they get hot? Because the air in a balloon, which is of course a gas, consists, like all gases, of molecules flying about in every direction. When you've got zillions of gas molecules doing this, they push quite hard against the inside of the balloon. That's why its skin is stretched so tight. When the sun makes the molecules hotter, they go faster, so they bounce harder and more often against the inside of the balloon. This pushes the balloon outwards and makes it bigger. Hot molecules take up more space than cold molecules. It's as if a lot of angry wasps were buzzing about inside the balloon. The hotter they become, the faster they buzz. And the further out they push the sides of the balloon. All of which boils down to saying that when a gas gets hot, it takes up more space. It expands. On the other hand, if you let a balloon get very cold, the reverse will happen. It will become quite a bit smaller. Because the colder the air molecules become, the slower they move. And the less they push against the inside of the balloon, which can now squeeze them into a smaller and smaller space. Cold molecules take up less space than hot molecules. The colder the wasps become, the slower they buzz, and the less room they occupy. In other words, when a gas gets cold, it contracts. Do solids and liquids also expand when they get hot and contract when they get cold? Well, you'll remember that if solids get hot enough, they melt into liquids. And the hotter liquids get, the more quickly they evaporate into gases. That's clear enough. But what's not so obvious is that before the change of state takes place, in fact, as soon as the solid or liquid starts to get warmer, it does begin to expand a very small amount. This is because the faster the molecules move, the further they pull apart from each other, both in a solid and in a liquid. That's why a space is always left at the top of bottles to allow for expansion in case their liquid contents should become too warm. A bottle should never be filled to the top, in fact, because if the liquid inside it gets too hot, there's even a danger of the bottle exploding. Can you think of an everyday example of a solid expanding and contracting? Well, what do you think causes that ka-thump, ka-thump noise when a car drives over a bridge? It's the wheels running over the spaces that have to be left between the slabs of concrete in the road to allow for expansion in the summer and contraction in the winter. So now you know not only why cars go ka-thump on bridges, but also how to prevent bottles from exploding and balloons from bursting. Or do you?
All right, write a paragraph summary about what it said about expansion and contraction, please. All right. Tell you a little story. You know, I served on a battleship. big guns. Barrels on the main battery of a battleship, 16-inch gun battery, are about 70 feet long. But if you looked in at a turret, turret kind of looks like this, and the gun extends out the front, but the gun also extends about 2/3 of the way into the turret. What you see on the outside is maybe about 2/3 of the actual barrel. The other third is inside. And at the end, where the muzzle end, where the bullet comes out, it's about this much in diameter. 16-inch, the whole 16 inches, and then like that. Down here inside the gun, where the gunpowder goes off, it's like 6 or 7 feet in diameter. And it goes through, if you looked at the front of the turret, what you would see are 3 oblong holes. And this barrel barely fits through the holes. I mean, it's not like they can open it up because the front part of the thing is 22 inches thick of solid steel. It's called a glacis. So it's a piece of solid steel that's about yay thick. Almost 2 feet thick. And that's meant so if a shell hit the front of it, it wouldn't get in. This is okay until you have to replace a barrel. We never had to replace a barrel in the Missouri. But the New Jersey, which was also stationed in the same place we were, Long Beach, needed to replace a barrel because they had the inside of the barrel was cracked. So they had to replace one of their barrels. Now, mind you, this is about 1984. No one had replaced a gun barrel on a battleship since World War II. In other words, the guys who had last done this, many of them were dead. Well, it's 40 years. I mean, these guys were around, or they were very old, but no one had done this in about 40 years. So they started doing this, which was fine. Now, remember, this is Long Beach in the summer. So they started in the morning, and they pulled the gun barrel out. But as the day wears on, it's LA in the summer, it gets hot. The barrel started to expand. As they got the new barrel in there, it got part way in and got stuck. Half in, half out. So basically what they had to do, see what just happened, they had to wait until the evening when it cooled down. They basically said, okay, there's nothing we can do. They figured this out that we just have to wait till the evening when it cools off and they finish their job. So there was a learning curve. But during the day they had half the barrel hanging in off this crane and half in. I mean, this is kind of a big